Let us take a look at the diode-IV relationship again. Notice this value VZK. This is where the reverse bias region ends and the third region, the breakdown region, starts. This is when the magnitude of the reverse voltage across the diode exceeds the threshold voltage called the breakdown voltage. This is different from the threshold voltage in forward bias. Notice that at this voltage VZK, the graph is shaped like a human knee. The K in the subscript is for knee. So what is the Z for? When we exceed voltage beyond VZK, what happens is that electrons move from the N to the P type via the external circuit. This causes the depletion region, see here in brown, to widen as more of the positive charge is uncovered with more electrons leaving the N region. The depletion region widens and the barrier voltage rises, causing the diffusion current to decrease to zero. However, unlike the reverse bias case where the depletion region stops getting wider, we continue to pump out more electrons out of the N region, further increasing the width of depletion region. This is the breakdown. This continues until a high junction voltage appears and a new mechanism is needed to continue supplying the reverse current. One of two breakdown mechanisms come into action. If the breakdown voltage is less than 5 volts, then the breakdown mechanism is called the Zener effect. This is what the Z means in the subscript of VZK. When breakdown voltage is greater than 7 volts, then the effect is called avalanche. For voltages between 5 volt and 7 volt, the effect may be both Zener and avalanche or one of the two. This all depends upon type of PN junction material, structure, etc. Remember that all these voltages are magnitudes of the breakdown voltage. Zener breakdown occurs when the large electric field in the depletion region starts breaking covalent bonds and generates electron-hole pairs. The electrons are swept into the N side by the electric field and a reverse current is generated. In Zener effect, what is different from the reverse bias condition is that a large number of carriers can be generated, but the junction voltage increases negligibly. The reverse current is now dependent on external circuitry. This makes the diode operating in breakdown region very suitable for operations where voltage regulation is to be established. In the avalanche effect, the covalent bonds are broken by collision. Part of the kinetic energy is passed on to the newly liberated carriers. They collide with another atom and generate another carrier. This bears resemblance to an avalanche as a large number of carriers are generated this way, supporting any reverse current with a negligible change in voltage drop across the junction. This part is similar to the Zener effect. So what is the limit to which we can increase the reverse voltage? The process does not destroy the device as long as maximum specified power dissipation is not exceeded. This is the safe limit which determines the maximum allowable reverse current. We will study Zener diodes and their application in future lessons in this module.